All right, so we have to have a little more variety because not everything is a homonuclear diatomic molecule. Let's talk about heteronuclear diatomics. But again, we're just going to stick to the second period. So it has to be a combination of something that is in the second period of the periodic table. When we are putting together our MO correlation diagram and our pictures, the things that we need to think about are now also including the energies of the atomic orbitals. So when we put them on the diagram, the more electronegative atom has a lower energy atomic orbitals. We will also have to choose whether or not we use a first order diagram or a second order. So which one do you use? If both atoms would use the same in their homonuclear versions, then use that. So cyanide, or any version of carbon and nitrogen bound together. Carbon and nitrogen are both in the first half and use second order correlation diagrams in their homonuclear diatomics. So we would use a second order correlation diagram in the carbon nitrogen heteronuclear diatomic version. So carbon and nitrogen, both on the same side, uses the same you would use for C2 or N2. If they have different versions in homonuclear, use the first order diagram. So NO, right? Nitrogen is in the first half, oxygen is in the second half. We're going to use first order. Now, there are, of course, exceptions. If there's an exception, I will tell you that it is an exception. Now, I might not explicitly say this uses second order or this uses first order, but you will have enough information if it is an exception. So, as an example, carbon monoxide is an exception. The way that I would tell you that is that I'd probably say something like it uses the C2 ordering, which is right. So carbon and oxygen, carbon's in the first half, oxygen's in the second half. You might expect to use a first order diagram, but then I tell you it's an exception. We use the same as C2, so first half means second order. So carbon monoxide, it's an exception. It uses a second order MO correlation diagram. That just refers to the energy orderings of those two levels in the molecular orbitals. So let's put together an MO diagram so that you can see it all in one spot. I've got an energy scale. I've got carbon atomic orbitals on the left, oxygen atomic orbitals on the far right, carbon monoxide MOs in the middle. The energies of the atomic orbitals are not identical, right? The more electronegative atom has lower energy atomic orbitals. So when I put in 2s and 2p for carbon, both of those will be at higher energies than the 2s and 2p for oxygen. And it should be very obvious that they're at different energies when you write this on your assignments. I still have the same things overlapping. So I still have a 2s and a 2s that make a sigma 2s MO and a sigma star 2s MO. With the p orbitals, I still get the pi 2p's, and this is a second order diagram. My pi 2p's are the lowest energy in this section, then the sigma 2p, then the pi star 2p, and then the sigma star 2p. Now, what will happen as you do this, because the bonding MOs are always lower in energy than any of the atomic orbitals that made them. The anti-bonding MOs are always higher in energy than the atomic orbitals that made them. Because of this, right, we've got an anti-bonding at higher energy, a bonding at a lower energy, with atomic orbitals at very different energies, you will find that bonding MOs are closer in energy to the more electronegative atom. And the anti-bonding MOs are closer in energy to the less electronegative atom. So I have what I mean here, I mean on the vertical scale. So I have a set of orange arrows showing the distance between, energetically, the distance between carbon atomic orbital and the sigma star, and the oxygen atomic orbital and the sigma star. So shorter arrow by carbon, carbon atomic orbitals are closer in energy to the antibonding, and it was less electronegative. Oxygen is more electronegative. Its atomic orbitals are closer in energy to the bonding MO than the carbon atomic orbitals. I mean, let's do a bond order for this carbon monoxide. You end up doing half of 8 minus 2. This gives you a bond order of 3. And if you compare it to the Lewis structure, you do get a match. Now I have the Lewis structure of carbon monoxide here. It's not pretty, we don't like it, but this is the best Lewis structure for carbon monoxide. The formal charges are not happy looking. However, we had to give everybody an octet. It was a priority role to give everybody an octet, so we did. That is my MO correlation diagram for this heteronuclear diatomic. Now let's talk about the pictures of the heteronuclear molecular orbitals. Because the atomic orbitals start out at different energies, they don't contribute equally to each molecular orbital. The MO will have a greater contribution from whichever atomic orbital it is closer to. So the closer energy means a greater contribution. It just means we drop bigger in the picture. For carbon monoxide, let's go through these examples. So now the sigma 2s, it's the 2s orbital on carbon, the 2s orbital on oxygen. You bring them together. This is a bonding picture. It should have a bigger contribution from oxygen, which was more electronegative, which means I'm going to draw it bigger in the picture. So what used to be a very symmetric drawing looks like it has been blown up on the right side, right? I have a bigger contribution from oxygen because they were closer in energy. And then I get the opposite for the sigma star. So sigma star 2s, bigger contribution from carbon. So I'm going to draw the s orbital on the carbon side bigger in this picture. I also now have to label which orbital goes with which atom. So you are also required to put the carbon and oxygen atoms, some kind of indicator showing which side is carbon, which side is oxygen. For sigma 2p, greater contribution from oxygen, which, right, this is now super awkward to draw, but this is what's happening, right? I have a regular p orbital on the carbon side. I have a regular p orbital on the oxygen side, but bigger because it gives a bigger contribution, and they have a constructive interference overlap in the middle. Sigma star 2p, antibonding, bigger contribution from carbon. And then in my pi interactions, my pi 2p, one set from the py's, one from the set of pz's, bigger on the oxygen end in the bonding, and then my pi star 2p's bigger on the carbon end in the anti-bonding.